How did our universe come into existence? Super-Kamiokande has been trying to get to the bottom of this fundamental mystery. Super-Kamiokande was completed in 1996. It's been leading the world in research on tiny subatomic particles called neutrinos. A 1998 discovery was even recognized with the Nobel Prize in Physics. Super-Kamiokande, which is celebrating its 30th anniversary in 2026, continues to evolve. Let's trace its journey so far and look at what lies ahead. In Gifu Prefecture's Hida City lies the town of Kamioka. Super-Kamiokande is located 1,000 meters beneath a mountain. From the entrance, it's a 1.7-kilometer drive down an access tunnel. Here's the doorway to the experimental area. Inside is the Super-Kamiokande control room. Here, observational data is monitored around the clock. Further inside the facility is a large dome-shaped area. This space is actually directly above the Super-Kamiokande tank. Let's take a special peek inside. The tank is filled with pure water, cleansed of almost all impurities. Here's what the inside looks like when the water's been drained. The tank is 39 meters in diameter and 41 meters tall. Super-Kamiokande uses this massive container to detect neutrinos, which are extremely small. Atoms are the building blocks of all matter. At the heart of every atom lies the nucleus. An atomic nucleus is composed of protons and neutrons, subatomic particles that are made up of even smaller elementary particles called quarks. Neutrinos are another type of elementary particle and are known for having no electric charge. When a star reaches the end of its life and explodes in a supernova, it produces vast quantities of neutrinos that are released into space. Our own sun also produces a large number of the particles along with the energy it generates. Neutrinos are also produced when cosmic rays from space collide with the Earth's atmosphere. Even at this very moment, countless neutrinos of all types are raining down upon us. In fact, it's said that the number that hit the palm of your hand every second is in the trillions. But because neutrinos pass right through most matter, we normally don't notice them at all. So how do you detect something so elusive? The key lies in the large amount of water that fills the Super-Kamiokande. Neutrinos from space rain down into the detector tank. On rare occasions, the particles may collide with the electrons or atomic nuclei inside the water molecules. When that happens, a faint flash of what's known as Cherenkov light is emitted. Using 11,000 photomultiplier tubes mounted inside, the detector captures that light, making it possible to determine the neutrino's direction, energy, and type. Each photomultiplier tube is 50 centimeters in diameter. They are so sensitive that they could detect a light as faint as a flashlight on the surface of the moon. Super-Kamiokande is able to detect elusive neutrinos thanks to its massive water tank and world-class technology. The history of Super-Kamiokande goes back to its predecessor, Kamiokande. In 1987, Kamiokande became the first in the world to detect neutrinos from a supernova. It showed the particles could tell us things about the universe that were unobservable through light.
充電完了。発破。
Construction on the Super-Kamiokande began in 1991. Its water tank would boast a volume of 50,000 tons, roughly 15 times that of its predecessor. Mounted on the tank wall were photomultiplier tubes that would deliver world-class sensitivity. And so, the Super-Kamiokande was completed in 1996, and observations soon began. One of the new research topics the detector has taken on is the study of neutrino oscillation. Neutrino oscillation is a phenomenon in which a neutrino switches from one type to another as it travels through space. We currently know that neutrinos come in three types: electron neutrinos, muon neutrinos, and tau neutrinos. For a long time, one of the biggest questions in particle physics was whether neutrinos had mass. Scientists predicted that if neutrinos did have mass, they would be capable of oscillating, that is, switching type. And so experiments were conducted at Super-Kamiokande to determine whether that was the case. They focused on muon neutrinos, which are produced when cosmic rays collide with the Earth's atmosphere. Observations revealed that the number of muon neutrinos moving upward through the Earth was about half the number moving downward. The production of atmospheric neutrinos should be roughly equal on both sides of the Earth. And given their nature, the neutrinos should be able to pass through the planet with ease. So, why were fewer arriving from the other side than from above? The reason was that the muon neutrinos from the other side had traveled far enough to oscillate into tau neutrinos, which are more difficult to detect. As a result, Super-Kamiokande observed fewer muon neutrinos coming up through the Earth. And so, the phenomenon of neutrino oscillation was established, proving that neutrinos did in fact have mass.
Professor Kajita.
The breakthrough challenged the standard model of particle physics and was recognized with a Nobel Prize in 2015. Super-Kamiokande's discoveries didn't stop there. In 2001, scientists published findings on the number of electron neutrinos produced in the Sun and confirmed that they also oscillated into other neutrino types. In 2009, they launched the T2K experiment, where they observed a neutrino beam generated 295 kilometers away by the J Park Accelerator in Tokai Village, Ibaraki Prefecture. They found that muon neutrinos can also transition into electron neutrinos. With that, Super-Kamiokande had succeeded in observing all three types of neutrino oscillations. The T2K project is now working on an experiment that involves sending beams of neutrinos and their antimatter counterpart, antineutrinos, to Super-Kamiokande. They're attempting to detect the differences between neutrino and antineutrino oscillations. What this experiment aims to do is shed light on the fundamental mystery of how our universe came into existence. Scientists theorize that the Big Bang produced equal amounts of matter and antimatter. But our universe today is almost completely made of matter alone. The antimatter has vanished. The T2K experiment aims to identify the difference in properties between matter and antimatter by comparing neutrino and antineutrino oscillations. From there, they hope to discover why our universe became so dominated by matter. And now, near the Super-Kamiokande facility, construction has begun on a next-generation experimental facility. This is the Super-Kamiokande project. Its tank will hold 260,000 tons of water. It will also feature enhanced photomultiplier tubes, double the number, in fact. The project is expected to advance our understanding of fundamental mysteries related to the dawn of the universe, including the differences between the oscillations of neutrinos and antineutrinos and the long-sought detection of proton decay. While certain efforts will transition to Super-Kamiokande, Super-Kamiokande continues to implement new upgrades. Since 2020, they've been adding a rare earth element called gadolinium to the water in the tank. This has reduced background noise and enhanced sensitivity to antineutrinos produced in supernova explosions.
ガドリニウムを導入すると、反電子ニュートリノの捉えやすくなるので、超新星爆発がどっちからやってきたとかいうことを探す際にも感度が大幅に向上することになります。
Our universe was shaped by the matter created and released by supernova explosions. The original Kamiokande was the first in the world to detect supernova neutrinos in 1987. But as no new explosions have occurred in and around the Milky Way since, further supernova neutrinos have not been observed. With Super-Kamiokande, scientists are working to detect potential future supernovae with unmatched sensitivity. They also hope to become the first to detect what's called the diffuse supernova neutrino background, which is the accumulation of neutrinos from all past supernovae.
この新星スーパーカミオカンデなら、今まで誰も見たことのない宇宙の姿を映し出せると思っています。
Super-Kamiokande has been at the forefront of scientific discovery for 30 years. How did our universe come into being? Super-Kamiokande will continue to lead the way in cutting-edge research.